Hey guys, so let's discuss new topic today from MLOps playlist. And so you can see, you can go to my channel and go to playlist section, and you can see all the playlist I have created. And in each playlist I have created lots of videos, so you can target particular playlist and complete that. Okay, so now in today's topic, we will be talking about auto-scaling AI workloads. Okay, so now let's talk about what is auto-scaling here, what is AI workloads here. So see, auto-scaling means you just increase or decrease AI infrastructure based on the traffic and or the load. Okay, so whatever how many requests are coming to your application, to your model, you will just increase or decrease AI infrastructure, means number of GPUs, and then VRAM, not VRAM, number of GPUs and memory and everything, right? And then what is AI workloads? So the system who is using these AI resources is called AI workloads. Okay, so here is the thing. Okay, so auto scaling means auto scaling means automatically increasing or decreasing AI infrastructure based on traffic or load. Okay, and then AI workloads, so any task that uses AI models and consume GPU CPU resources is called AI workload. So whatever projects you are making, let's say, okay, notification system, chat GPT kind of application, they all are AI workloads because they are using AI resources. Okay, mm, now let's see some examples of AI workloads. That is, first is LLM inference. Okay, like ChatGPT answering a question, user questions. So that system you can call AI workloads. And then model training. Okay, so training a new language model billion, and then um, training a new language model on billions of documents. So billions of documents are there, and you are giving it, you are giving this document to model, and okay, as a training, for the training, so that next time when you ask some question, he will get answer. Okay, he will have the answer. So, and then third one is fine tuning. So fine tuning is customizing a model for healthcare or banking, let's say. Okay, so customizing a model means model was already there and it will have some weights also. Okay, you have already trained that model on some parameters, some documents, some resources. Okay, Wikipedia pages or everything, you have just trained that model. Now you wanted to train that model according to your specific domain requirement, let's say healthcare. So you will modify the behavior of the model there. Okay, so that is the fine tuning. Now then, embedding generation, so creating vectors for document search, RAG. Okay, so this one is you're just putting a document. Okay, let's say you're storing document in a vector database, and we know that we store text as embeddings. Embeddings is nothing but the number of you can say number array. Okay, number array like 0.21 0.22 or dot 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 something. Okay, multi-dimensional array. And then image generation, so creating image from text prompts. Okay, I have given ChatGPT a text that give me YouTube thumbnail for this video, and this is the content. So he will create a image from that. Okay, so that is also AI workload. Then video generation, so let's say I wanted to edit some video, and I have given that tool a text. Okay, so it will generate that text to voice recordings. Okay, and then means not recording, but in that video. And then speech to text, so converting meeting audio into text. So like when we do Google Meet, you get that meeting notes, right? So what it is doing, it is doing that, this only, speech to text. Then text to speech, converting text into spoken voice. Okay, and this video generation is converting video from text description. Okay, and this is the text to speech, what I was talking about earlier. Now recommendation system, so suggesting products or movies for, let's say, for Amazon, for notification. Okay, whenever you search for some product, you get similar products, okay, on your screen. So that is the that's coming from the recommendation system. And then computer vision, so detecting object or defects in a image or video. So now AI workloads are expensive. Why they are expensive? Whatever projects you are making in AI, whatever model you are making in AI are expensive. Why it is expensive? Because they are using GPUs, and GPUs are costly. Okay, and then traffic is unpredictable. So how much traffic? Let's say you have 100 GPUs, but you don't have that much request. So in that case, your GPUs are getting wasted, right? uh, your money is getting wasted. Or let's say you have only 10 GPUs, but you have lots of requests, so your GPUs are not sufficient to cater all the requests. Okay, and the latency will increase. Then in that case, you will definitely have some queue there, queue system which will hold your request, but you will have a latency there, right? So it will again cost you. So traffic is unpredictable there. Now inference is compute heavy. Okay, whenever inference is compute heavy means I have a model, I have asked a question to a model, so directly the request will not go to model. There will be an inference layer, which will, let's say what it will do, it will take the GPU, it will load the model weight into the GPU, and then that request will come to this inference model, this GPU, and then that inference will give the tokenized response to the user, and then he will manage lots of things. Okay, so now, so what auto scaling is helping here in this system, so it will reduce your cost. Okay, let's say at night time the request is lower, let's say 10 request is coming, so there is no use of using let's say X number of GPUs, right? You can reduce GPUs at night time, and then you can increase GPU at daytime when the traffic is more, right? In that case, you can have a huge cost saving, and then handle spikes suddenly. Let's say in a big billion day sale, okay, suddenly the request number of request means the number of request spikes. Okay, so in that case, like millions of requests I'm getting, so in that case it will automatically increase the number of GPUs, let's say. Okay, and but you cannot directly increase the GPU, and then request cannot directly go to that GPU. It will take some time because you need to load weights in the GPU, and lots of background processes are there which will take around 30 seconds to minutes time also. So in that case, we use the concept of warm pool. So you will keep a few GPUs ready. Okay, and whenever a request spikes, you will just divert that traffic to those GPUs. So now we will see all these things in this video, and then improve latency and avoid GPU overload. Okay, so you will have a sufficient number of GPUs, so the GPU overload will not be the problem. So now the next thing is high level architecture. Okay, so first user request will go to load balancer, and from here it will go to inference router, because you can have multiple models. Okay, and now which model you need to use? So inference router will route your request to there. Okay, and then it will get the GPU port. Okay, and the GPU, your request will go to GPU ports, and then from there it will go to LLM inference. Okay, LLM inference will send the response back to user. I told you that LLM inference will do all this request response, tokenize, streaming tokenizing, and then all this work. So now autoscaler monitors what it will monitor. So it will monitor traffic, how means how many requests is coming per second, and then it will check the latency, that how much time it is taking to send the response to a user. Then queue size, so your request, then your queue will come, and then your GPU system will be there. So all the requests will go to queue. Okay, so that GPU will not overload. And also, if auto scaling required, we will just set a we'll set a rule on the queue, that if the queue size increases, then just go and then increase the number of GPU. That is how we will come to know that we need to increase the number of GPU, or we need to decrease the number of GPUs. Now GPU usage also. Okay, if GPU is means the 80% utilization is happened, then just create a new GPU. Okay, so and dynamically scaling pods. Okay, so create a number of pods, then increase or decrease number of pods. So now why AI auto scaling is hard here. See, in the normal web application, when we talk about there, if you need to auto scale, what you do there, you just increase the number of CPU and increase memory, right? But here you need to increase you need to work on lots of things. Okay, so like AI systems additionally needs GPU memory, token throughput, model loading time, and then inference latency. So I told you that model, so like you have created GPU, new GPU, now you need to load that model weight into this GPU, and it will take means 30 seconds to several minutes of time. Okay, and then your inference latency also. So inference system will also take some time to send the response, and also all these latencies will combine. Okay, so that's why it is hard. Auto scaling is hard here. Now, types of auto scaling, if you talk here, so it is horizontal scaling, vertical scaling, and then Kubernetes HPA. Okay, so Kubernetes side, it is automatic. It will scale your application because Kubernetes is a infrastructure. It will manage your infrastructure. Okay, it is a orchestration tool. So now, types of auto scaling, the first one is horizontal scaling. So what we do there, we add more pods or nodes. Okay, so in my Kubernetes crash course, I have explained that you will have a node, and a node means system, normal servers, and then inside a node you will have a pods. Okay, and then GPU resources and all is associated to that node. Okay, like two GPUs I have associated this node, and then let's say I need to run a model. Okay, those models will run into the pods. So I have a several models, and I wanted to run one model which required 10 GPUs. Okay, it's a very complex model. It's a very heavy, compute heavy model. I required 10 GPUs for that. So Kubernetes will choose for me which node my pod will create it. Okay, and then it will just create my pod on that node because GPUs and all these resources are associated to that node. Okay, so that is the thing. Horizontal scaling, so add more pods or nodes. So for example, if 2 GPU pods to 10 GPU pods is required, okay, like traffic spikes, so it will add 8 GPU pods automatically. So this is the most common approach. Okay, so here we are increasing GPUs. Now what is the vertical scaling? So in vertical scaling, it will increase the machine size. Okay, so now you are using a small GPU, so you will go and use the larger GPU. Okay, who will have the VRAM, whose VRAM is large now, or other things. So now that's common for large scale AI application. Kubernetes auto scaling. So this is HPA. HPA is horizontal pod auto scaler. So here automatically scale the pods. Okay, so this is the most AI systems use Kubernetes, I told you. Now, for example, if high traffic, then it will increase inference pods. Okay. Now, metrics used for AI auto scaling. So I wanted to do auto scaling, and then what all metrics I will be using. I told you that traditional system will use CPU memory, but AI system, okay, AI system will use now GPU utilization. Okay, it will check how much GPU has been utilized, and then request per second, how many requests are coming per second. What is happening, just a minute. Okay, then it will check request per second, and then queue size. Okay, and then token per second, how many tokens generating per second, and then TTFT, so time to first token, how much time it is taking. So example, like GPU utilization is greater than 80%, so add more GPUs. This is what I told you. Queue-based autoscaler also. So I explained this also. Okay, very common in AI application. So what will be the flow here? Flow will be, yeah. So flow will be, if the traffic spikes, so request queue grows. Okay, so the queue where your request is going, so if it will grow, then autoscaler adds number of GPUs. Okay, so useful because GPU startup is slow. I told you warm pool we will be using, and then request buffered safely. Okay, now problem. So what is GPU cold start here? So GPU pods take time to start. Okay, why? Because it will load the model. Okay, and then CUDA initialization, and then downloading waits. Now what is CUDA initialization? See, it will take 30 seconds to several minutes. Now what is CUDA? CUDA stands for Compute Unified Device Architecture. Okay, so here it is NVIDIA's platform and programming model that allows software to use NVIDIA's GPU for general purpose computing and not just for graphics. Initially GPUs were designed for graphics, but now you will use it for the general purpose computing, and you will use that using the CUDA. So this is your application, let's say. Okay, you have created in, let's say, using the PyTorch, TensorFlow, LLM servers you have here. Okay, and then and then after that your CUDA initialization will come in between, and then NVIDIA GPU hardware. This is your GPU. Okay, so CUDA acts as a layer between application and GPU. So what is the solution here? So see, the solution is warm pools. Okay, so keep some GPUs. So what is the solution here? Warm pools. Okay, warm pools means keep some GPU pods preloaded. For example, two warm strained by GPU pods reduce latency spikes. Now, model loading challenges. So large model like 70 billion plus parameter model. Okay, so its size could be hundreds of GB, let's say. So large loading model repeatedly is very expensive. So what is the solution? So use the shared storage, okay, or model caching, let's say. Mm, or persistent volume you can also use there. Okay, so now multi-model auto scaling. So what is multi-model? You have a multiple models. Okay, it's not about one GPU. Now you have a multiple GPUs. Now how you will do auto scaling for multi-model? Okay, so different workloads may need different models. So let's say you have in your application you're using FAQ. Okay, so it requires a small model. Coding related thing required a large model, or searching related thing required an embedding model. So you just independently you scale the models there. Okay, so autoscaler scale each independently. Now GPU sharing. So sometimes workloads don't need full GPU. Okay, like so you can use MIG and fractional GPUs. So MIG means multi-instance GPUs, and fractional GPUs also. So multiple workloads will get assigned to one GPU only. Okay, so it will improve your utilizations. So for example, one GPU shared by embeddings also, and then lightweight inference also, let's say. Now continuous batching. So what is continuous batching? Modern inference system like vLLM or TensorRT LLM. Okay, this is the example of continuous batching models. Okay, so batch request dynamically. Okay, so they batch the request dynamically. So first of all, we are sending not the single request to GPUs, we are sending in a batch. But let's say one batch is completed, okay, and then again new request came, so it will not wait, that request will not wait, it will just get dynamically added into the existing batch. Okay, so what will be the benefit would be higher throughput and fewer GPU needed, right? So huge cost saving, let's say. Now predictive AI auto scaling. So yeah, so now predictive auto scaling. So advanced system predicts traffic ahead. So just traffic ahead, like today I'm gonna launch, like today Apple iPhone is gonna launch. Okay, so definitely the traffic spikes will be higher, and traffic will spike, and then you in advance only you auto scale your infrastructure. Okay, for example, traffic usually spikes at 9 a.m. So scale before a spike happens, and then multi-region auto scaling. So global AI systems deploy multiple regions. Okay, so definitely we deploy systems in multiple regions. Okay, in US, in India, and everywhere. So it will. So what is the benefit? We know that latency would be lower. Okay, because the request will get served from the nearest region server data center. And then disaster recovery also, if India's data center have some issue, so you can divert your traffic to US data center. Okay, from there the request, it will serve the request. For example, US traffic use US GPU, and India traffic will use the India GPUs. Now cost optimization. So GPU infrastructure extremely expensive. Okay, so auto scaling helps avoid idle GPU and reduce cloud bills also. So like for example, without auto scaling 100 GPU always running, and with auto scaling 10 GPUs at night. Okay, so means 100 GPU during peak time. So it will huge saving. Okay, your cost, it will save your cost. Now important metrics. So GPU utilization means we are using for the efficiency. Okay, and then queue length. What is happening here? Just 2 minutes. Yeah, so now the next is queue length. Let's say queue length we will be using for the pending request. Okay, all the pending requests would be there in queue length. So using queue length you will find that how many requests are pending. Then TTFT, so response So now TTFT response start latency, okay, time to first token, and then TPS token per second, pod startup scaling delay, okay, pod startup time, how much time the pod is taking to start, so that is your scaling delay, okay, how much delay it is taking if you scale the system. Now example AI auto scaling flow. So what will be the example? So user traffic spike, let's say, okay, so your queue size will also increase, so auto scaler will get triggered automatically, and then it will launch some new GPU pods, and then it will distribute the traffic. So now what challenges we will be facing here, okay, in auto scaling? So slow GPU startup, so I told you, you just go and use warm pools, okay. Then expensive GPUs, so just go with the dynamic scaling, okay. And then traffic spike, so queue based scaling, and model loading delay, so cached model, okay, just have some, use the cached model. And then idle resources, so scale down. If the request is lesser, then just scale down, just decrease the number of GPUs. So now real technologies you use for let's say for pod auto scaling, we go with the Kubernetes HPA, because lots of people use Kubernetes. And then queue based scaling, just go with the KEDA. And then for metrics, go with the Prometheus. For efficient inference, go with the vLLM. And for GPU partition, go with the NVIDIA MIG, multi-instance GPU. So for example, production architecture, if you see here, so user request will go to API gateway. From here, it will go to inference router, which will select the inference model which it has to use. And then request will go to that particular queue. And then GPU workers will work on that queue. Okay, the request will get assigned to GPU workers, and then streaming the response. Okay, inference model will stream response to user. Autoscaler monitors GPU usage, queue size, and then latency, and on based on this metrics, it will do his work. So that's it. Thank you.